Hi, everyone, and thank you so much for joining us. This is the fourth webinar in our series, NOAA Fire Research from Conditions to Impacts, hosted by NOAA's Climate Program Office in partnership with NOAA's Fire Observation Research and Services Team, or FOREST. My name's Clara Deck. We have other organizers on the line today, Monica Kopach and Shiv Das, also from the Climate Program Office. And first, I'd like to introduce Monica Kopach, the Program Manager for the Atmospheric Chemistry, Carbon Cycle, and Climate, or AC4 program here at CPO, and she will give us a couple words of introduction today.
Thank you, Clara. Welcome, everyone. It's my great pleasure and great excitement to welcome you to today's edition of the webinar, which is focused on more of the impacts of fire, particularly air quality impacts. In fact, if you're familiar with science fact sheets that NOAA puts out, I'll put it in the chat. There's one on air quality. So I know we have a broad audience and not everyone works in air quality, so this is a little bit more. And this is a great example that we have today. So the two talks we have today represent jointly a field campaign that NOAA had about 2016, 2019, FireX. I won't talk about what our distinguished speakers will talk about, but I do want to mention one other aspect of this effort was that it was a great collaboration between NOAA scientists and external scientists, both of whom are represented today in our talks. And this is where Climate Program Office comes in, hopefully making those connections and making them successful. So just real great pleasure to have both Karsten and Bob today talking. So without further ado, thank you so much for joining, and please enjoy and think of questions.
Yeah, thank you so much, Monica. So as you just heard, today we're going to hear from two scientists, Karsten Warnecke from NOAA's Chemical Sciences Laboratory, and we'll also hear from Bob Yockelson of the University of Montana. So during the webinar, at any point, please feel free to use the question feature in the GoToWebinar panel to submit questions. And if you're comfortable doing so, please indicate your name and your affiliation with your question so that I can let the speakers know that information during the Q&A sessions, which I will facilitate after each presentation. So to start off, we are going to hear first from Karsten. Karsten Warnecke is a research scientist at NOAA CSL, and his program today will focus on the FireX-AQ campaign findings and gaps. Thank you so much for being here. I'll let you get your full screen going. It looks great. And go ahead and take it away, Karsten. Thank you.
Thank you, both of you. And yeah, as you said, my name is Karsten Warnecke, and I work for the NOAA Chemical Science Laboratory. And I was the science lead for the FireX campaigns. And today I'm going to summarize some findings and also mention some gaps that are still existing. So I will focus on emission, chemistry, and a little bit of modeling and impact as well. So we had two campaigns, Fire Lab and FireX-AQ. And as I said, I'll talk about emissions and processes specifically. So what was FireX? It was a large-scale field campaign that was a multi-agency, multi-year effort. Between 2016 and 2019 is when all the measurements were done. And in subsequent years, up to now, a lot of data analysis has been done. You see here all the platforms that we used during FireX. The main platform was maybe the NASA DC-8 aircraft that we basically rented for this campaign, but we had two other NOAA aircraft, the Twin Otters, one with a chemistry payload and a Met Twin Otter, remote sensing, mobile laboratories, people on the ground. So we had connections to the satellites. So we did a really holistic study with boots on the ground, measurements in the atmosphere up to remote sensing with satellites, all working together to get a really holistic picture of fires, emissions, and their impacts on people. So let's start with the Fire Lab, which was measuring smoke composition. So this was an AC4 funded project. So thanks to Monica and Shiv for that facilitating this really large-scale experiment to look at smoke composition. We had a lot of instruments in the fire lab where you basically simulate or make a small fire and really can measure the composition in great detail. And fire lab probably was the most detailed composition measurement of fires that has ever happened up to that point. The second part was the FireX AQ flights with the NASA DC-8 and the Twin Otter aircraft. Today I'm going to focus mostly on the DC-8 since I can't go into all of the details of all the other aircraft. But working on the DC-8 captured the most fires at that point. This was an effort that was really supported by AC4. So some of the instruments that flew on the DC-8 were funded by AC4. So I think that already shows you the good synergy that we have between the different NOAA programs and how appreciative we are of the AC4 program and the Climate Program Office. So FireX had about 90 papers published so far. More are on the way. And today I'm just going to show a couple really highlights here. And the first one is just looking at the flight tracks on the left that you can see. They're color-coded by CO. So every time you see large values, that's where fires were. They're indicated in the letters. And on the right, you see the typical way we flew these fires. So the DC-8 had remote sensing capabilities as well. So we flew over the smoke plume and looked at the plume that way, and then really followed the plume downwind and then measured the emissions and the evolution of those plumes. And I think you all know by now that if you live in the Western US, or these days on the East Coast, like New York, you live with fires and you live with smoke. During FireX, we had the opportunity to look at a lot of different fires. We had 14 Western fires, lots of ag fires, and different biomes, different fuels as well. So let's start with the emissions. And I'm going to focus on the total emissions. On the bottom, you see that pie chart. And as you can imagine, most of the emissions are CO2, CO, and some carbon-containing compounds. And those are many, many different species. But for the first couple of slides, I focus on the gray part. So CO2 and also CO, so the total carbon emissions. So step one, how much carbon is emitted from fires? So to do that, there are various ways. One is shown here. So the CT, the total carbon, you can calculate that from looking at the burnt area, from the biomass density that was there, from the fraction of biomass consumed, and the fraction of carbon in the biomass. So a lot of those data you get from satellites, for example, VIIRS, MODIS, or also GOES FRP. Another method is just you looking at the FRP, so that's actually the fire radiative power. So the brighter that fire is, the more emissions you likely will have. So there's ways of using that product to get the total carbon. But what's shown here is for that Williams Flats fire, basically looking in detail at these four terms that you need to know and get the time series of the emissions by looking at the satellite data and calculating that out. I have to say this is very labor intensive, so that's not something you can do for every fire in the US. So you can do that for some specific fires. So using that method, we get a time series of total carbon emissions. So with the aircraft, of course, we get that as well. I said earlier, we fly over the fire to look at the shape of the plume, and then we fly through the plume to get the concentrations in there. And if you use these two things together, you can actually integrate through that plume and get a total carbon emission as well. And since we did this multiple days in a row at multiple times of the day at multiple differences, you also get something like a time series. So the two methods are shown at the bottom here in this time series of the carbon emissions. And you can see they really agree pretty well. So the fuel to fire inventory, as we call it, is the boots on the ground method, where we looked at the burn area, and then the aircraft measurements in red on top of that. And they actually agree within the error estimates, which is something I call actually a large success. So here is now the comparison of these two methods, specifically our measurements to all the emission inventories for that Williams Flats fire on 3 different days. And now you can see there's huge, I should call this probably disagreements, or a huge range of what the inventories think the emissions were. Of course, these inventories, some of them are really large scale, they're global, some of them are on smaller scales, and they give you a daily average value. So you're not always comparing apples to apples, but I think this makes very clear that we still do have a long way to understand the total emissions of fires like this Williams Flats fire. And on the right, you see that for different days, it's actually different for this one fire as well. So the models tend to either over or underestimate this, but there's also huge variability from day to day. And I should point out here that in the US and in parts of Asia, we have geostationary satellites where we actually get better diurnal coverage than in the past. But we only get that for parts of the world. So this is missing everywhere else. But again, we made good progress and we have some good comparisons, but there's definitely lots of work left to be done in total carbon emissions. So here's the next step. So now we're looking at this tiny little sliver. That is the smoke that you actually visually see when you see a fire plume. That includes particles and many, many different gas phase species. A lot of those, almost all of those are carbon containing. Some of those are also have nitrogen in them. But this is the tiny sliver. And if you look at what's burning, you understand already a little bit what those sliver could be. Here is a quick showing of what the chemical composition of biomass is. So biomass is cellulose, hemicellulose, and lignin. And those are really large straight chain polymer compounds. And all I want to say is here, the carbon fraction is about 50%. There's a lot of oxygen in it, some hydrogen, and a few percent of nitrogen. But you can imagine when this material with these long chain molecules burns, you will get a large variety of compounds emitted. So it's also that there is a really complexity to this, not only by the stuff that's burning, but also how it's burning. So you see pictures here of flaming, gasification, pyrolysis, and what usually happens, it's a mix of these processes. And each of these processes will emit different compounds. So I think these pictures demonstrate already that there will be a very large complexity to smoke itself. So in this picture here, it's a 2D GC chromatogram. So this is an analytical technique where basically every dot you see in there is a different compound that has been detected. And in this chromatogram by itself, there were over 800 different compounds detected. Not all of them are identified, but some of them can be classified into these different groups, like oxygenated compounds. That's small oxygenated are the largest emissions. But there's aromatics, there's polar compounds, and many different ones. So over 800 compounds have been observed in, this is for one fire from the fire lab that I talked about earlier. So large complexity, large variety, but here's a little bit of good news. So fire XAQ, these are the flights now in this case, compare really pretty well to previous missions. So in each of these scatter plots, it's a comparison to a previous mission or a lab mission or other aircraft or compilations of previous data. And there's really a decent comparison, but these are log-log plots, and you can see that even on a log-log plot, there is quite a large variety, especially if you look into detail of these highly oxygenated compounds, as you see in these bottom graphs. There is a large variety of these emission factors that we now look at. The next step, of course, is how to parameterize those for models. You cannot put 800 different compounds into a model. And also, you have to adjust for the fire stage. I showed you flaming versus smoldering. And the current way of doing this is by the modified combustion efficiency, which basically is looking at the CO2 to CO ratio. And it's a little bit of measure of how efficient combustion is. The more CO2 and VOCs is emitted as well, the less efficient the pyrolysis or combustion is. For example, if you have an engine, like in a car, combustion is much more efficient than in biomass burning. So if you plot the emission factors here on the right versus the modified combustion efficiency, there's often a good correlation between the two, but it's only for some of the compounds this works well. Shown here is methane, where it actually works pretty well. For others, it doesn't work all that well. But overall, this is the way we currently do it in models. During the Fire Lab experiment, we actually tried to find a new way of parameterizing these emissions. And I showed you the complexity of the biomass that's burning and the different temperatures that it's burning at. And what you see here on the top is that if you're looking at lower temperatures compared to higher temperatures, what you get is at high temperatures, you really break the material that you're burning down to much smaller molecules, like in this case, shown here is benzene. At lower temperatures, you don't break down that material as much, and you get compounds like, it's called syringol, so there's a lot more functionality on this benzene ring left over at these higher temperatures. So basically, the higher the temperature, the smaller the molecules are. So, and we're trying to use this as a different way of parameterizing. So this was done here in a paper by Kanako Sekimoto that looked at the high temperature versus low temperature. And on the left, you see a mass spectrum. So each stick in there is one compound that we measured with one specific instrument. And at high temperature, this mass spectrum looks quite different than at low temperatures. So now we use the ratio of these two factors and compare that to the fire radiative power that we measured from a satellite product. So this is from the GOES geostationary satellite, where we have 5-minute data to look at that ratio. We did this for the FireX fires. The Williams Flats is in red. Other fires are in the different colors. And you do see a pretty good relationship between that ratio to the fire radiative power. So that slope that's shown in that graph on the right now can be used as a different way of parameterizing the VOC composition of those emissions. So we can use satellite data to get the total emission, and now we have also a way to use satellite data to get a better way of getting the composition understood. So to summarize this part, we definitely have obvious gaps. So for example, this new parameterization that I just showed, we have really almost no experimental validation that works. There's still a lot of different compounds that we haven't identified, and we definitely don't know the evolution of all these different compounds that are emitted and what they do downwind. So let's talk about the downwind impacts. So I showed you that the fires themselves and the emissions have a huge variability, but here are a couple pictures of smoke and the variability in those. So the picture in the center shows one fire plume, a plume from one fire. We can see that there's smoke in the lower areas. That's from one part of the fire that was more from smoldering combustion. And then there's a smoke plume that's from the flaming that lifts the smoke up higher in the atmosphere. Once it cools down, it makes a plume that then gets transported to faraway locations. On the bottom left, it's in the early morning where smoke has filled up valleys completely. There's no plume that's transported far away. And on the right, there's again a smaller fire showing you that it can just fill up areas very local. So there's a huge variety of these different fires as well. So the meteorology, the fire stage, emission ratios, transport and chemistry is really pretty variable. But I'll show you that we got a little bit more handled during FireX on some of this variability. So ozone downwind is now highly variable. On the left is a plot from Bob Yochelsen's group who will talk in a second here after me, showing that ozone production is really extremely variable downwind. And some fires you have a lot of ozone production and some almost none. And as I said, there's a lot of variability. It's the metrology, it's the fuels, it's the flaming versus smoldering that actually changes the emissions. The emissions changes the VOC to NOx ratio, which is one of the chemistry metrics on how ozone is formed. So, and then there's other factors as well. How thick is the plume? How much sunlight is available to kickstart chemistry? So in thick plumes, there's less light, so chemistry will go slower. On thin plumes, chemistry will go a little faster. So all these different variabilities is something we did measure during fire XAQ on these different fires. And we used all these data to build a box model framework that you see here on the left. So we have the fuels, metrology, and also the emissions. We did a much more detailed chemical analysis of the smoke than has been done before, which led us to be able to add more chemistry to these models themselves, while recognizing that there's still a lot of missing reactivity in these fires that we still don't capture with our model. But this is probably one of the most sophisticated models to date, because we have these really wonderful data from the fire XAQ campaign. So we modeled 2 different fires. One was the Williams Flats fire, which was a very large, humongous wildfire, and the Blackwater fire, which is a very small prescribed burn in the Florida Panhandle in very different conditions, meteorology-wise and fuel-wise. So here are the results from this box model that I just described a little bit before. And don't worry, I'm not going to go into the chemistry that this model does too much, but I just wanted to give you a few take-home messages and show how this works. So on the left is ozone versus the physical time scale. So basically just the transport time. How old is the smoke in how long it's in the atmosphere? The Blackwater fire produced a lot more ozone in a very short amount of time, even though it's a much smaller fire than the Williams Flats fire. So you can see that. And that is because chemistry was going much, much faster in that plume. As I said earlier, the Williams Flats fire was so dense that there's very little sunlight available inside that plume that the chemistry is just going faster, because chemistry needs sunlight to get kickstarted. So now we have in the middle plot here plotted this ozone versus the chemical timescale. And you can see versus the chemical timescale, which means how fast the chemistry goes now is taken into account. These 2 fires are actually relatively similar, even though they're in very different sizes. So now we already found a way to get to a more common denominator for these type of productions in ozone downwind. On the right is now also plotted versus the NOI. So the VOC to NOI ratio tells you how much ozone you can actually produce. The NOI that you have, the initial NOI, limits the amount of ozone that you can produce. So the Williams Flats actually had relatively little NOI, but it was very efficient by producing that ozone from that little NOI. So, and now on the right, it's plotted versus the initial NOI, and you see that the Williams Flats fire was actually very large in that respect. So just quickly summarizing here, we have now found a way with this box model to understand how fast the chemistry is going, so the speed, how efficient it is, and how much ozone we can produce in total from these various different fires if you take all the metrology, the chemistry into account correctly. So now we use this box model on a real world example. So what does smoke do when it hits urban areas? So this is actually data from after fire XAQ, but with lessons learned from that large field campaign. So this is data from Boulder, that's where I'm located right now, of measurements from ambient air in smoke-free, smoke impact from a more local fire, and smoke from long-range transport that we measured on 3 different occasions. So on the pie charts, you see the composition of the VOCs in these 3 different times, and you see the more biomass burning impact you have, the more oxygenated VOCs you have. This is what you expect. Anthropogenic emissions are less oxygenated than biomass burning is. And on the bottom, in the bar charts here, you see the VOCs, the CO, and the NOx. So NOx is not long enough lived that you really don't get much NOx from long-range transport, but it is emitted from anthropogenic local sources. So when you see in green, the NOx really doesn't change in these 3 conditions, but the VOCs specifically and the CO is really quite different in these 3 scenarios. And as I said earlier, the VOC to NOx ratio is really determining how much ozone you can make. So the top now shows there's three scenarios, a diurnal plot of ozone from the box model and the measurements. So the measurements in black and the box model in the three different colors for the three different scenarios. And on the left, you see the typical no smoke day. On that day, 30 ppb of ozone was made. Then you look in the middle, local smoke, that is also 30 ppb of ozone made on that day, but everything sitting on a much higher background. And this background is transported ozone. On the right, this is for the long range transport, a lot more background ozone and still maybe a little more than 30 ppb of ozone made on that. And that is because Boulder is NOx sensitive. So you do not, with the smoke, you do not bring more NOx into a city, but you're bringing a lot of more VOCs in it. And in an area that's NOx sensitive, that means NOx is actually relatively low. You're really depending on how much NOx you have. So even with more VOCs, you do not produce more ozone because you do not have enough NOx to be very effective at making ozone. So that's for Boulder. So is smoke increasing urban ozone is the title of this slide. Yes, it is definitely increasing urban ozone, but mostly because of transported ozone. But how about formation? So I said with Boulder, NOx sensitive, it doesn't increase ozone formation that much. But larger areas like Denver downtown or Los Angeles or New York City downtown areas, they're actually NOx saturated. That means there is a lot more NOx available to make ozone. And you see in the plots in the bottom of this, in the box model, we vary NOx and VOCs. And you really do see differences when you vary NOx. Not so much when you vary VOCs. So the green curve is the no smoke scenario. And if you add a lot of NOx, like what you would do in these downtown areas, you really would bring ozone up quite a bit. There's not a whole lot of data about scenarios like that where we have these plumes going into larger areas, but we do have some data from a campaign that we did in 2023. That's smoke in urban areas. We did see smoke in New York City, and the photo on the left bottom is actually from June 2023, where smoke was just hitting New York. And it's a daytime photo where you basically cannot see anything anywhere in the city. This smoke was so dense. This is, of course, something we haven't analyzed yet quite right. So this is for the future, but we do have some scenarios. But there are very few scenarios where we have these situations on how does smoke really affect people in urban areas from intensive campaigns. They're, of course, they're from like the monitoring networks. So as a summary, I think we've made really major progress during the Fire XAQ campaign, but there's still a lot of open questions left unanswered. And I want to point you to our website here and a couple pictures also from the Twin Otter that I didn't talk about. And I'm happy to take some questions. And I want to end with, again, stressing that the collaboration between NOAA laboratories, like the Chemical Sciences Laboratory that I'm in, and the Climate Program Office is really essential to get people like Bob Bjorkelsen, who's going to talk next, into programs like Fire XAQ, and we're really all benefiting from this large collaboration. Thank you.
Great. Thank you so much, Karsten, for that great presentation. Just to remind everybody, you can enter your questions using the question feature within the GoToWebinar panel. And if you feel comfortable doing so, please add your name and your affiliation to your question so I can share that with the speakers. So I'll give everyone just a minute here to organize their questions and get them into the question feature. And our next talk will be kind of building on this and will be related, so we can also continue questions at the end if we want to move on to Bob and then do questions for everybody at the end. Does that sound okay? Great. Okay. So Bob, you are now the presenter, and so we can't hear you. You'll need to unmute your microphone. There we go.
Okay, it should be unmuted. I'm
Yeah,
gonna,
so here we are. Our next presenter is Bob Yokelson, a research professor in chemistry at the University of Montana. So Bob was partially supported by the Atmospheric Chemistry, Carbon Cycle, and Climate AC4 program for his work during the FireX campaign, which we'll hear about during his talk. And thank you so much, Bob, for sharing with us, and we're excited to hear. Go ahead.
yeah, can everyone see my slides at this point?
Yes, we can see them.
Okay, great. Well, thank you to Monica and Clara for organizing this. I'm honored and appreciate the opportunity to help describe some of the recent fire research. I'm also proud that I started my atmospheric chemistry career at NOAA as a postdoc. So Dan Albritton was the lab director when I was a NOAA postdoc, and he used to like to explain our ability to understand the atmosphere using this triangle here. So in the lab, you can isolate and precisely measure important atmospheric reactions between various chemicals, et cetera. And then you can put all that information in a model of the atmosphere and predict, for instance, if the atmosphere has a specific composition at one time, what it should be at another time, say time B. And on a grander scale with good emissions inventories, you could predict, for instance, how the Earth as a whole would respond if the amount of fires doubled from the present day. However, the field measurements are perhaps most critical because that's how we check if the models are failing for some important chemicals or even completely missing things that should be added to the model. So now let's muck up our nice little triangle by adding rapidly changing amounts of energy and rapidly changing mixtures of compounds from fires. The relative atmospheric, physical, and chemical properties are going to interact with each other in numerous ways. So for instance, the weather affects the amount of available fuel, the ignition probability, the moisture, chemistry, and geometry of the fuel. And then the fuels impact the dynamic mix of combustion processes. And that in turn affects the chemistry of the emissions and the smoke injection altitudes and other things. And all those factors impact how the smoke evolves in the atmosphere at different levels in numerous ways. And eventually we get to air quality impacts for much of the Earth, if not most of the Earth. So to better understand this complex system, NOAA, as you saw, has world-class expertise in a lot of these variables, such as fire, weather, and measuring chemicals in the atmosphere. But no single agency has world-class expertise in everything. But fortunately, the NOAA Atmospheric Chemistry, Carbon Cycle, and Climate Program, aka AC4, gives NOAA the ability to add expertise on a temporary as-needed basis to optimize the research projects. In 2014, in response to increasing fire impacts and public concerns, NOAA scientists like Karsten, who you just heard from, carefully decided to carry out a large-scale fire research project, which he described. And as he said, phase one involved sampling smoke at the Missoula Fire Lab. And then a phase two was more on sampling smoke from aircraft and fixed and mobile ground-based labs. And to support this, AC4 created a competition for funding to support the NOAA effort. And that resulted ultimately in 20 awards. I've just listed the first 10 here. And those all contributed findings to phase one of FireX and beyond. And I'll give examples of that next. But first I'll explain why phase one was at the Fire Lab. Karsten used this earlier version of this slide he made to, this is an earlier version of the slide Karsten made, and he used it to illustrate the wide variety of instrumentation. And I'm using it just to show some of the inherent strengths of lab research. So in the lab, as we mentioned, you can characterize the fuels better. You know the plant species, you can know the fuel moisture, chemistry, size distribution, you can vary the geometry, etc. And you can manipulate the fuels so you can see what the effect of burning an isolated component is, but you can also generate realistic mixtures. And so as a former wildland firefighter who's looked at a lot of fires, I also hired 2 forestry grad students to help us simulate really realistic fuel mixtures. Another benefit of the lab is you can capture all the smoke from a whole fire. And also, this is really critical. We've shown that the smoke is well mixed at the height of the sampling platform, which is about 50 feet above the fuel bed. And the reason is that's critical is it allows you to combine data from different instruments. And so that is useful in itself, but also useful for testing new instruments in a realistic sample matrix against previous techniques. And then finally at we have a custom OpenPath FTIR system that's custom made to span the whole stack at the sampling platform and provide real-time measurements of CO, CO2, and 22 other gases that can be inorganic or organic and arising from flaming or smoldering combustion. And we also set up equipment to provide real-time black and brown carbon, the single scattering albedo, the angstrom absorption exponent, or AAE, and emission factors for absorption and scattering by particles. So now some examples of what we learned, and I'm going to have to break the rules of a good presentation here. The results are spread out over probably about 50 publications. And so I can't show a graphic and full attribution for all these studies, but I'm going to try to mention them all, hopefully not forgetting anything, so you get a feeling for how widespread the research was. And so I'm going to basically explain this list, but I'll come back and show some pictures in a minute. By manipulating the fuels, it was apparent that the fuel diameter had more impact on the bulk of the emissions than the tree species. For instance, if you burn a large diameter log of any tree species, or duff, which is compacted organic material, that promotes a much higher smoldering to flaming ratio. And the choice of species mainly just impacts smaller variation in the mix of smoldering compounds. But on the other hand, this work in the fire lab, combined with later urban monitoring of smoke in the Bay Area, showed that you can get insights into the fuels due to indicator species that are unique to various shrub and tree species, for instance, from spruce or manzanita. And this has implications for emission inventories that currently use static vegetation maps or land cover types, and I'll explain that more in detail. Another big advantage is knowing the nitrogen in the fuel. Because we know the nitrogen, we can also measure its fate in the emissions and basically construct a nitrogen budget. Another project measured the isotopic signatures of NOx, HONO, and particle nitrate from pure biomass burning, and then later used that in field work to determine the fire contribution of these important compounds in areas with multiple sources of those species. And the most important oxidant in fresh plumes is the nitrogen species nitrous acid, or HONO. And the HONO to NOx ratios are really highly variable in the initial emissions. And one clue we observed in the lab was that high canopy fuel moisture was associated with high HONO to NOx ratios. And we also tested new instruments for total particle nitrogen, and that instrument also measured organic carbon, and we tested a new instrument for particle morphology. Because we were sampling well-mixed smoke with multiple instruments, we made a lot of progress understanding how to interpret all the instruments' results. For example, proton transfer mass spectrometry cannot a priori assign relative amounts if multiple compounds have the same exact mass. Now, GC and 2D GC can separate species with the same mass, but those techniques have the problem that some compounds in smoke are too sticky to measure on a column. So in that latter case, we see more total signal at a specific mass on a mass spec with that has a specialized inlet to get those compounds into the instrument. But in many cases, probably the majority of cases, the GC data can determine the splits for exact masses measured on the mass spec in real time. So we learned about both techniques and much more about smoke than we could have by operating these instruments solo. The mass assignments that we developed for smoke mass spectra in the Fire Lab have basically been widely adopted by the community in subsequent work. That's a very highly cited paper. And we made a few improvements to that based on the airborne measurements. But and one other thing is in the well-mixed smoke, we were able to use the FTIR data for formaldehyde, ammonia, and HCN to effectively calibrate these species on the mass spec, and those are otherwise really difficult to calibrate. When it comes to smoke optical properties, in addition to measuring the emissions of black and brown carbon, we also carefully intercompared the different techniques for measuring black carbon. And we found substantial differences that are detailed in the paper. Some studies identified many of the individual brown carbon compounds, and those are the individual species that absorb UV light. And they also measured their detailed absorption spectrum in their lifetime against photolysis. Another study simulated cloud processing of smoke, and one team found evidence for an absorbing aerosol type that would actually be intermediate between black and brown carbon in properties. The lab smoke that was used in several state-of-the-art artificial aging experiments. So think of smog chambers and mini chambers and such, oxidative flow reactors. The lab emissions also gave insights into questions about smoke age and evolution in the field data in ways that we didn't originally anticipate. And to explain that, in the lab, we know the vertical velocity in the stack, and we know the initial emissions measured on the platform are 5 plus or minus 1 seconds old. But in the aircraft studies, it fires up to several, well, in aircraft studies of smaller fires, you can still sample directly over the flames at 100 to 200 feet AGL and get initial emissions that are less than a few minutes old. But measuring emissions less than an hour old on a massive wildfire is pretty difficult. And so the physical age of the near source samples is a little uncertain. We can't measure the vertical velocity of the emissions in the convection column before they level off in the plume. And even then, the plume can be poorly mixed. And I'll show a picture of that. That makes representative sampling ambiguous. So, but our best estimate is that the freshest airborne samples had often been aged already for 1 or 2 hours. So several of the model studies of the evolution of the airborne sampled plumes actually found the lab data helpful to estimate what we call the time zero composition. And in fact, one of the NOAA twin otters got this really beautiful, unique measurements of nighttime smoke evolution. But since they had a smaller payload on that plane, they had to use the lab data to estimate initial values for some unmeasured species that they needed in their model. Another point about new data, lab data, is it revealed high levels of a number of VOCs, such as furans, that had not been included in previous models of smoke evolution. And when these VOCs were added to model runs, they had significant impacts, including increasing the modeled ozone formation. And those findings were later validated by the airborne studies. We're almost going to finish this list. So the The lab data more recently was used to parameterize the original NOx emissions as a function of fire combustion efficiency in a way that extended to fires that have high combustion efficiency and high global significance, but we couldn't sample them during FireX AQ with the aircraft. And finally, the lab data was used to parameterize the initial variability in the ratio of brown carbon to carbon monoxide. And that helped interpret the results from smoke plumes that were sampled from the aircraft, but only at the downwind end where their age was like several hours to several days. And Karsten talked about the PMF, and I'll just mention that it was useful for modeling the VOCs and the nitrogen emissions in the smoke. And then later in the airborne samples, when you add an aging factor, and we even found this PMF, very similar factors were useful in determining the wood smoke contribution to the pollution in Fairbanks in our next big project. So some pictures for you again. You saw this picture before, and the point I'm going to make is that, for instance, by looking at the fire and watching the emissions, you can see what emissions come from which process. And so looking at the gasification process, the ammonia emissions only kick in as soon as the gasification starts. And so for this reason, all the fires are videotaped, and those tapes were made use of by several scientists. Here's a plume that's reasonably well mixed at the source, as I talked about. And here's one where it would be really hard to choose a location to say, here we measured the initial emissions representing the whole fire. And for adding new compounds on this slide, the red shows the total ozone made in the model. Black shows the ozone made just from furan as a precursor. And you can see that in the early part of the fire, the furan's accounting for as much as 15% of the ozone production. And even at the end of the simulation period, when the furan's mostly gone, it's still accounting for 5%. And that's pretty impressive for just one compound out of hundreds of VOCs. So now on to the field measurements. Karsten covered this in more detail. And I have to mention that at this point, NSF and NASA were also providing funding on a really generous scale. So instead of making you listen to me read through a whole list again, I'll just say a little bit about the object topics in red, which are ground-based monitoring station, integrating airborne and ground-based data in some products that came out of that. So as motivation for deploying mobile labs, the upper left here, this shows a smoke-filled valley in central Idaho. That's from a Forest Service lookout webcam. And so you can see, obviously, it would be very dangerous to try to fly an airplane to sample in there. But down here, you see there's 4 mobile labs, sampling under that dense smoke layer. And so in all, I better go back here. In all, about a dozen towns or fire camps were sampled day and night. There was real measurements of hazardous air pollutants measured directly by Aerodyne, and a lot of data on the PM impacts, the brown carbon, reactive oxygen species, which are important health relevant topic, and even some interesting observations about how smoke is transported in complex terrain. So these are all nice outcomes from having mobile labs, and they often sampled smoke from the same fires that the aircraft did, and you could compare that smoke. Meanwhile, as one of the fixed ground sites in Missoula from 2017 to 2021, this is funded by both AC4 and NSF, various aspects, for 5 years and over 1,500 hours of smoke impacts in Missoula. we measured black carbon, brown carbon, CO, PM, ozone, NOx, etc., in what I would call regionally representative surface smoke. And for 2 full years, we also got the hazardous air pollutants, courtesy of my colleague Luhu at who was funded by NSF, the weekend program. And so what that looked like here, the red dot is where our lab is, where we set up the monitoring. And the patches where there's you can see where the fire burned up here, upwind about 10 miles away. That's from the fire that I showed in my title slide. And then this graphic over here shows that the back trajectories from the main Missoula smoke peaks confirm that we're sampling a large upwind area, so we call it regionally representative. Some of the observations are still being used. We're evaluating how well the models predict the hazardous air pollutants. And then some of the results from that are already published. And what we saw in Missoula was that ozone was usually enhanced above the clear sky ozone in dilute smoke, but suppressed when we got hit by really thick smoke. And that's consistent with what Karsten was saying about the lack of light needed to make ozone. We got some measurements of the brown carbon lifetime, and we saw one episode of nighttime production of brown carbon due to urban wildfire interactions. But frankly, we thought we were going to see more, so that was interesting that it wasn't that common. The PM during that time ranged from 0 to 471 micrograms per meter cubed. And the PM to CO ratios were really interesting. We found that ratios around 0.01 to about 0.03 were typical of smoke-free days, but smoke-impacted days were always had a ratio near 0.12. But then in the aircraft at 5 kilometers in smoke 0 to 40 years old, there was not a trend in the PM to CO ratio, and it was much higher. So here's a look at that data. The high elevation measurements are here, and the ground-based data here includes all this Aerodyne Mobile Lab in Missoula ground-based data we had at the time. And all the subsequent Missoula measurements and ground-based measurements we found in the literature since then are consistent with this pattern. And then a really cool thing happened. We had a chance to sample a plume that was descending, and that's pictured here. The brown is the smoke, the blue is the flight path. And as the aircraft descended, the temperature changed from 285 to 300. And so what we saw in the data was that normalizing species to CO to account for their dilution, black carbon to CO did not change, and that's consistent with its thermal stability. But the organic aerosol in green, the levoglucosan in blue, and nitrocatechol in red, they all decreased, normalized to CO, consistent with their volatility. And the implications of this are significant because for radiative forcing, you get impacts from the entire aerosol column, but those impacts are the highest at the top of the atmosphere where light encounters them first. And also a lot of long range transport happens you get long range transport of smoke to urban areas, and that often occurs at those high altitudes, colder altitudes. But then the smoke mixes down during the day, and you actually you don't change the smoke, but you change the PM health metric, which is interesting. But also the mix of gases changes substantially. And so that's important, and I'll talk about that a little bit more in the future stuff. And also NSF lends support to a major effort led by Kelly Basanti that integrated a lot of this new emissions data from FireXAQ, WeCan, and other work into a new database for modelers who want to use the latest estimate of ecosystem average emission factors and ratios. And Karsten mentioned the OH reactivity. This slide shows from uh, past times to about 2019 when the work was just being completed to now when we integrated it all. This is the increase in the total OH reactivity. So this is symbolic of the fact that we basically at least doubled the information that we have about smoke with these recent campaigns. In addition, some of Karsten and I and many of the others from NOAA and NSF supported projects, we were invited to share our perspectives on what we learned and set directions for future research. So,
Bob, I just want to let you know you have just about a minute.
okay, so all right, so here we're just I won't talk about this much more again, but these new non-methane organic compounds that we see are going to evaporate from PM. A lot of those are hard to measure, and so we're going to need some method development and more measurements in age smoke in the future. Uh, for for health effects, there's still unknown air toxics that we need to discover. There's synergistic effects between pollutants that we don't understand. And maybe the most important promising thing would be to combine bottom-up exposure measurements with top-down metabolomics. I'll try to get through this quick. This is an example of measuring the fuel conditions and the weather on the ground back in 2004 when we didn't have a lot of satellite data on this. Here on the left is many of these relevant satellite uh, fire weather and fuels data that's available. The right shows how well they were coordinated and correlated. And then here, the authors who did that work also measured the emissions on all those fires where they compared the in situ and remotely sensed data. And you can see that with just a few of those satellite products, they were able to get a very good fit to the combustion efficiency and actual emission factors. So to conclude, uh, we don't, fires are relevant to a lot of really complex factors. We don't really know what the next priorities will be, but there's a lot of potential and they're all complicated. So I'll just leave this here for a minute. I think we need to be in the scientific community, maintain or enhance the core expertise and continue collaborations and that sort of thing. And so I'll take questions if there's any.
Great, thank you. Thanks for that great presentation. We do have one specific question for Bob, and I think Karsten can come back on screen if we can take some overall questions about FireX too. So we have a question, Bob, I think you mentioned a study in the Bay Area related to species impacting emissions. Do you recall what that study is? Somebody's wondering about that.
Oh, yeah, I think it's Alan Goldstein's group or Kelly Bersanti, perhaps a joint thing, but they were able to see tracer species that species in the smoke that they know only come from Manzanita, which is a type of chaparral plant. And earlier, Kelly's group had shown that uh, the volatiles in the canopy produce unique compounds. So like the oils in a spruce needle will give you a unique signature in smoke. So, and
Great.
that if they contact me, I can get the exact paper to them. So.
Okay, great. And that person said thank you and amazing presentation. So maybe we're getting close to the end here, but we can end with a general question that is for both Bob and Karsten. Are either of you aware of or involved in upcoming field efforts on wildfire smoke, and specifically on the wildland-urban interface?
Um,
Well, I could go first quickly. We just submitted a proposal to measure the WUI fire emissions, from burning houses, in collaboration with the Missoula Fire Department. And we have a new mobile lab from NSF EPSCoR funding, and that's one of many applications that we hope to pursue in the future.
yeah, we currently have no mission on the books, but we are starting to plan for future missions, and a fire study is definitely going to be one of the main targets that we will do, hopefully within the next 5 years or so. And NASA is doing the same thing, actually. So they have Inspires planned. This is more for piracy bees, but that's of course fire related. And then they're also thinking about a study maybe a good 10 years after fire is probably a good turnaround time.
Oh, great. Yeah, thanks for that info. We have reached the end of our time here, and thank you to our speakers again so much for your time today and your great presentations. The recording of this webinar will be up on the Climate Program Office website within a week, we hope. But I put up a couple of our future webinars here. We're excited to host more webinars in this series. Our next one is on September 17th, and I put a link in the chat for you to find more info on this and the registration links for our future webinars. So thank you again to everybody who joined us today, and we hope to see you next time.
Thanks.